Look at these images. Have you ever wondered how water can lift a container ship weighing thousands of tons? We're looking at one of the biggest and most amazing hydraulic engineering projects in history. It connects the Pacific Ocean to the Atlantic Ocean with a navigable channel, literally cutting a strip of land, the current Panama, from northwest to southeast with the aim of significantly reducing navigation times between the two oceans. Yes, we are talking about the Panama Canal, considered the eighth wonder of the modern world according to the American Society of Civil Engineers.
But how does this megastructure work? Let's take a look.
Ciao ragazzi, this video was written and filmed in Italian by our team of scientists, storytellers and video makers. We are Italians. It was manually translated into English, but dubbed with artificial intelligence. Long live culture, and let's go back to the video.
The first attempt to build the canal dates back to the end of the 19th century, when the Frenchman Ferdinand de Lesseps, I hope that's how it's pronounced, after successfully building the Suez Canal that connected the Mediterranean to the Red Sea, sought to construct a similar project on the other side of the world. Although the Panama Canal was 40% shorter than the Suez Canal, its construction was much more of an engineering challenge because cutting through Central America meant encountering a combination of rainforests, tropical forests, humidity, and dangerous animals. Consider that where the canal begins, on the Pacific side, the workers' first challenge was to create an opening at the summit of Mount Culebra, 110 meters above sea level. The workers excavated 14 million cubic meters of rock with dynamite and steam-powered mechanical shovels, bringing the elevation of the cut to 59 meters above sea level. Basically, imagine sawing into a mountain to open a passage through its center. I mean, it's virtually insane. However, an important detail was not taken into consideration by the canal designers. The workers were unprepared for the hardships presented by this type of tropical climate, and many fell ill with yellow fever and malaria. This situation, just imagine, led to the death of about 20,000 men. For this reason, the French company failed, causing investors the loss of approximately $207 million. In the early 1900s, US President Theodore Roosevelt opted to assume control of the French undertaking, providing a sum of $40 million to sustain its progress. However, the government of Colombia declined to cede a portion of its land as it was unwilling to give up its sovereignty and control over the territory. But, in order to achieve their own goals and to undermine the Colombian government's authority, the US supported a movement that had long sought independence from Colombia and the creation of a new state. In 1903, Panama declared its independence, and the United States of America achieved its goal of obtaining a perpetual license in the canal zone. The engineers made an insightful choice. To avoid excavating tons of rock to access the Atlantic Ocean, which would have required a huge workforce and an enormous amount of money, they decided to construct an artificial lake to transport the ships a distance of 33 kilometers. To do this, they raised the Gatun Dam, which blocked the Chagres River and caused the flooding of thousands of hectares of land in the area in which the large artificial lake is now located. Today, Gatun Lake is crucial for the functioning of the canal, as it supplies the millions of liters of water necessary for the operation of the locks. But what are these locks? The locks are hydraulic engineering structures that enable a vessel to overcome a difference in elevation. This is the key engineering aspect of the Panama Canal. The boat, coming from the sea, enters a chamber delimited by two rather sturdy gates. From the part where the water level elevation is higher, water is pumped through valves towards the lower level, enabling the boat to ascend until the gate of the higher level opens and the boat can continue its journey along the waterway. Brilliant! To exit the canal, the reverse operation takes place. The boat enters the chamber at the highest water level elevation. The water is then drained out, which brings the ship down to a lower level. The locks practically behave according to the principle of communicating vessels. They're basically elevators. The lock chambers, look at them, are massive blocks of concrete with sidewalls that are 15 meters thick at the base and 2.5 meters thick in the upper section, where the water pressure is evidently lower. Below these chambers, there is a system of tunnels and valves where water flows to fill and empty the lock. Just imagine, it takes a total of 1,000 cubic meters of water to lift up a vessel of those dimensions. We're talking 40 to 50 Olympic swimming pools. A vital element for the correct operation of the canal are what they call mulas, which means mules, and it is not by chance that they are given this name. The mules are small electric locomotives that move along the tracks adjacent to the locks, ensuring the smooth and successful passage of ships from one lock to another within the waterway system. Their primary responsibility is to secure the ship's passage along the middle of the lock, thereby preventing any potential collisions with the gates and walls. Usually 2 locomotives are used on each side for large ships. The first 3 locks of the Panama Canal work exactly in this way and have done so unchanged since the early 1900s. It is unbelievable. A total of 1 million ships and 300 million tons of goods have passed through the canal. In 2006, the Canal Authority initiated construction on 2 larger locks, one on the Pacific side and one on the Atlantic side. These locks, which are 100 meters longer and 20 meters wider than the original ones, can accommodate larger ships, which are known as new Panamax vessels. These ships have the capacity to carry twice the load of a Panamax vessel. However, given that each ship requires 100,000 cubic meters of water, it is evident that the addition of new locks meant that the biggest risk was that the extra traffic could dry up the lakes. That is why the new systems have been designed with the addition of side basins which retain 60% of the water used in each passage, so it can be reused in the next cycle, namely when another ship passes by. So, while 100% of the water used in the old locks ended up in the sea, with the new system only 40% of the water does. With the new system, the new lock also uses less water than the old one, about 7% less, and that's 7% of 101,000 cubic meters. If they use the canal, ships traveling from Pacific ports to Atlantic ports and vice versa don't have to circumnavigate South America, which in turn saves an estimated 3 to 4 weeks of time, a significant amount of fuel, and of course helps reduce carbon dioxide emissions. Thanks for watching our latest video. See you again soon here on Geopop Everyday Science.
A presto, ciao!